Today is May the 11th. This is Addison Shonnet at AirInsight. My guests are Brett Starbuck, who is Assistant Director of Advanced Concepts at Pratt & Whitney, and Vince Sidwell, who's the Director of Advanced Concepts and Technology, I hope I got that right, at Pratt & Whitney. Gentlemen, thank you for visiting with me today.
Thank you for having us.
So the reason I wanted to talk with you is because Pratt has come out with this thing called HySIITE. Is that what am I saying that right?
It's right. It's the hydrogen steam injection intercooled turbine engine concept.
I don't know who thought of that name, but so just to get like sort of a background as how we get there. Pratt & Whitney came up with the first water injection engine, right?
I'll say we came up with the first hydrogen engine back in the 1950s, if that's what you're referring to.
Well, there was also water injection at some time ago.
Yeah, so jet engines have done water injection for decades, right? As a way to increase power for takeoff. So water injection has been pretty well known, even in the industrial turbine world. Water injection is used today, but this is a little different use of water injection, more for efficiency than for just power increase.
So I guess I just wanted to mention the fact that injection, the concept of injecting stuff into a fan engine is not brand new. The idea is obviously has got some history. So could you explain to us the concept of hydrogen propulsion technology, please?
Well, we have to be careful because we're mixing some metaphors. So HySIITE does a couple of big things. One is it does involve water injection at some different places in the engine, but it also leverages the unique properties of hydrogen to make that a very efficient system. And Brent, I'll do a quick summary and you can give some more details. So we use water in 3 places in the HySIITE configuration. We use it as an intercooling feature in the compressors to increase the efficiency of the cycle. We use it as steam injection in the combustor to increase the specific power of the combustor. And then we use it in the turbine section to add improved cooling to increase the cycle efficiency. All 3 of those things give us a more efficient cycle. What liquid hydrogen lets us do is it gives us a cold sink that lets us condense water out of the exhaust. And that's a very efficient way to get the water needed for these injection things. I'll also note that if you have cryogenic hydrogen, you can't burn cryogenic hydrogen in an engine. You have to warm it up, transition it to gas phase, and using some of the heat of the exhaust to warm it up to gas phase is another cycle benefit.
This is very complicated.
Brent, you want to provide some more details?
Yeah. I think at its most fundamental level, Vince alluded to this, the HySIITE engine is really trying to exploit all the various properties of hydrogen. So we really came up with an engine architecture and a cycle arrangement that allows us to do that. Because we have looked at just converting a off-the-shelf or legacy type engine to burn hydrogen, and you can do that. And it there's some good things that happen, but it doesn't really allow you to exploit all those properties that Vince just alluded to. The fact that you have a cryogenic sink, so you can do a lot of things with cold. You have some moisture in the exhaust, so you can do water recovery using that cold, and then we can inject it in various regions of the engine. And to your original query on water injection, that is something that goes way back into the earliest days of jet engines. Back when jet engines did not have much thrust, they would do water injection into the inlets of the engine and into the midsection of the compressors to boost thrust. So we are exploiting that principle in addition to using the cold to get and the moist properties of hydrogen to get access to water continuously during flight.
Yeah, it's probably worth saying one of the obvious benefits of hydrogen is it doesn't have a carbon atom, so it doesn't create any CO2. So by definition, it's a zero CO2 thing.
Yeah.
But we also think there are other benefits to emissions. So because of the properties of steam injected combustion and hydrogen combustion, we think the temperatures in the combustor will be lower, which will make less oxides of nitrogen, which are one of the engine emissions we worry about in altitudes. And we're exploring the potential benefits associated with contrails. Obviously, hydrogen makes a lot more water than burning kerosene does, but it burns very cleanly. And to make contrails, you have to have water and you have to have particulates. And the science is still a little early, but there might be some contrail benefits as well.
I like contrails, by the way. I love the look of them.
Well, they're pretty, but they are a radiative forcing impact on the climate. So they do create climate change.
Okay. Can you gentlemen explain to me what would be the use of this engine, or does it have a use across the board?
Well, it actually has use across the board. If you zoom way out, the HySIITE concept is a very efficient energy conversion method in a hydrogen economy. If I need to create mechanical work, a HySIITE cycle could work. Obviously, we make jet engines, so we're thinking about the jet engine application. But in a hydrogen economy, if you need to make some sort of shaft power, this is a very efficient way to do it.
In terms of the engine size that you're working on, in terms of thrust, can you walk us through? I mean, is there, you're going to build some kind of a working model, right?
Well, remember, HySIITE is a very, very early TRL project. We're at TRL 01 now, and we'll be at, I don't know, maybe 3 when we're done. So we're talking about doing some lab scale demonstrations of some of the components we need for the HySIITE engine, but it's short of building an engine. We do think it puts us in a position where we would be ready to propose some sort of experimental engine demonstration after HySIITE.
And is the technology involved reverse engineerable to any current engine, or do you have to, like, is this a clean sheet?
It's a clean sheet.
Yeah.
Brent talked a bit about you can put gaseous hydrogen into an existing jet engine, maybe with some combustor changes, but that's not a very interesting solution. This is a fundamental shift in the way we think about the cycle. Brent, go ahead.
Yeah, no, that's a critical point. You know, it is a different type of cycle to exploit those properties of hydrogen. So you can't just, you know, convert an existing engine to this technology readily. But with that said, this technology, it has some challenging areas, but it is not like on the science fiction edge of technologies. So through the HySIITE work that we're going to do, we're going to burn down some of the risk on some of the key components, some of the heat exchangers and technologies like that, in addition to the hydrogen combustor. And it's to get us to a point where you know, we achieve about a TRL 3, which is really saying it's feasible, it's kind of workable, but you don't really have the whole system demonstrated. And that would be the type of follow-on activity that we're trying to position ourselves for. So it's a very nice you know, contract and program that we have through ARPA-E, because it's allowing us to explore kind of the bounds of the problem in ways that, you know, normally we don't get to do, because it is a very different architecture and cycle. So ARPA-E has been you know, very, very bold you know, in allowing the industry to you know, propose in various areas, which we did.
But Addison, you remind me of another important point. So we can build a really efficient hydrogen engine out of HySIITE, but there are other things that are required for it all to work, right? Obviously, you have to have an airplane that has hydrogen fuel tanks and hydrogen fuel systems, right? It's not a bolt-on to an existing airplane.
That was my next question.
And of course, there has to be hydrogen infrastructure. There has to be hydrogen available at airports. And Pratt & Whitney doesn't make hydrogen infrastructure, and we don't make airplanes. So it is dependent on the rest of the industry catching up. But we do think one of our responsibilities is to talk about what's possible in a hydrogen economy. You know, what benefits we could get to if it did exist. And we think HySIITE is a nice example of what's possible.
So I'm trying, obviously I don't have any idea of what this thing looks like, but I'm envisioning a turbofan of some form on a wing. What, in the current environment, we know that there's a fuel tank that supplies the fuel to the engine, and that's how it runs. And in this particular example, you would have a tank with hydrogen. Would that hydrogen you'd mentioned before, that would be liquid to become a gas?
Liquid hydrogen, because gaseous hydrogen really would be inefficient for an airplane because it takes up an enormous amount of volume. So it'd look like a blimp. So you really want to pressurize and liquefy the hydrogen so that it's an efficient volume for flight.
When you pressurize hydrogen, you're not going to be able to put it in a wing.
That's correct. It will have to be in a cylindrical or spherical tank, likely in the fuselage, but that's up to the airframers.
Right.
You've
And
probably
what-
seen various pictures out there from the airframers, such as Airbus, that have
Right.
various images showing where a hydrogen tank could go.
But the
Right.
engine itself won't look that different from the outside, right? It will still be a geared turbofan. It's just inside the inner nacelle will be some additional.
Vince, you just said
right?
the magic word there. Going to be a geared turbofan?
Well, so HySIITE is really a play on thermal efficiency, and it's compatible with any of our propulsive efficiency approaches. We think the geared turbofan is the right solution to try to get better fan pressure ratio, bypass ratio, and propulsive efficiency, and that is perfectly compatible with the HySIITE engine. So our vision product would be a geared propulsor with a HySIITE engine on the back in a hydrogen economy.
Any idea of the thrust ranges that this would go from?
It can cover a wide range. It's really a question of, for long range and larger aircraft, how does hydrogen trade out on that? We think it will trade out potentially positive in the single aisle size. So that's what we focused in on. But, I think that becomes an airframer. They have to weigh in on that also in terms of what the aircraft architecture looks like at the bigger size.
Yeah, so certainly single aisle, probably down to regional jet size, like A220 size, things like that. Getting smaller than that might start to get a little challenging, but we haven't thought deeply about that yet.
Right. I'm fascinated by the implication, and of course, your engine people, but I'm fascinated by the idea, like you mentioned, Brent, about the examples we've seen so far that came from Airbus in terms of concepts. How much space and weight the hydrogen fuel tank is going to take?
Well, that's definitely a challenge. Through various studies and activities, we have seen that placement of hydrogen on an aircraft can result in an aircraft penalty. And really the theme of HySIITE is to bring enough disruptive engine performance to the table to offset that. And how that scale actually balances out is still to be determined. Initial results are very encouraging, but that's what we're going to uncover through this contract activity. But the underlying theme is you are correct. Putting a big hydrogen tank on the aircraft is a little less efficient use of volume. It's a little less efficient mass distribution. And the question is, can the efficiencies that we think we can gain through the properties of hydrogen offset that?
What does the timeline look like from, let's say, where we are now to seeing a working model of an engine like this?
Well, as we said earlier, so HySIITE will get us to, say, TRL3 with some lab-based component.
What does that mean in English?
Oh, so that means we've done a component level laboratory sized rig, right? Sort of proof of concept laboratory sized things.
Is that something you measure in years or months?
Oh, no, it's a couple years. Yeah, I think the HySIITE is 2 years.
Yeah, it's actually an accelerated program.
Yeah, and we think after HySIITE, we'd be in a position to write a proposal to do some sort of experimental ground demonstration. And I'll guess, but that's probably 4 or 5 years.
Mm-hmm.
So today plus, call it today plus 6 years would be an experimental ground demonstration.
Loosely, we're kind of targeting having the availability of a hydrogen type engine like this in the mid 2030s. Exact dates are hard to nail down, but we don't control that all ourselves, right? I mean, that's definitely going to be affected by the hydrogen economy. It'll be affected by how the airframers, but we're trying to be in a position with this technology to be ready, depending however the world unfolds.
It seems to me that this is not a crazy statement, that airplane design follows engine design.
Well,
in general, that's a true statement historically.
So if you are, the group you're with has a growing confidence that, let's say, the mid 30s, there's an engine available, when would an airplane OEM start thinking about, okay, this is going to be available by, let's say, 2035, do they start coming up with ideas of design around the 2030, 2032, 33?
So we're not an airframer, but I'll tell you, it takes a long time to develop a brand new airplane. And this would be a brand new hydrogen airplane. So the degree of difficulty is a little higher. But the other piece that we're all waiting for is the infrastructure piece. And that's a little bit new to our industry, at least for the last 100 years or so. So there has to be an industry that makes liquid hydrogen and delivers it to airports. So
that would seem to be like the smallest technology hurdle in this entire formula.
Well, technology certainly, but from an economic investment standpoint, that's probably the biggest hurdle, right? Creating an entire economy around liquid hydrogen.
How do they make liquid hydrogen now?
They cool it through a series of turbine expanders to make more and more cold until it liquefies.
Right.
So you're just going to scale that, really, right?
Well, yes and no. A lot of the ways they make hydrogen today are not very environmentally friendly. There are some new ways to do it. For example, for renewable resources, or things like hydropower. Sometimes they'll make hydrogen when the electrical demand is low. So hydrogen is a way of storing electrical energy effectively. But that doesn't really scale to the amount of hydrogen we need for aviation quite yet.
Right.
So there are a lot of, I'll say, policy related questions around what does a hydrogen economy look like?
Right. It's interesting that
I think one thing that's really important to point out, though, on hydrogen and the hydrogen economy is, there's really a finite number of paths the future can unfold. One of them is in the area of sustainable aviation fuels. And we definitely see that as absolutely critical in the transition process and with legacy aircraft. But that's essentially the realm of synthetic jet fuels. And they can be made through bioprocesses, or they can be made by creating hydrogen and combining it with carbon to make a hydrocarbon fuel. From a scalability perspective, I think the jury is out, but it's starting to lean towards the notion that at scale, you're probably into some type of hydrogen-based process to make a synthetic jet fuel. And then the question becomes, if you have that hydrogen economy in place to make the hydrogen to create a hydrocarbon fuel, are you better off taking that hydrogen and just liquefying it and burning it directly? That's a big question. We don't know the exact answer to that. And we'll see how the technologies unfold. But there is kind of this underlying thinking trend that is starting to emerge, that it's starting to look like elements of our economy, aviation in particular, may be very dependent on a hydrogen economy. It's just, how do we use that hydrogen on the aircraft that we're poking at from a technology perspective? And that's kind of an interesting view if you just step back and think about that for a second, because the hydrogen economy, that's probably when you were a kid and you read popular science and popular mechanics, you probably read stories about the hydrogen economy. So it is a different world, and climate effects and climate change is potentially changing this landscape.
It's fascinating when you think about the hybrid electric solution, which of course Pratt & Whitney Canada is quite deeply involved with, that goes up to a very specific size because batteries and everything else. Beyond that size, which let's say up to, I'm going to pick a number here, let's say a 65, 70 seater turboprop flying short range 300 miles. Beyond that, you have to go to some kind of fuel outside of electricity to make it work. And the longer the range airplane, so you've got to have SAF, like you mentioned. But in the end, you don't really have a choice. If you want green flying over distance, you need to have something like this hydrogen solution.
Well, Brent said it very famously a couple of years ago. In our future, we're always going to burn something. Because the Brayton cycle is very efficient. I'll point out, by the way, the Canadian hybrid electric program, it is hybrid. So it is a gas turbine coupled with motors and generators and battery storage.
Right.
And we see the same thing for larger aircraft as well. They don't have quite the percent hybridization that the Canadian program does, but there's a lot of advantage to hybrid electric. But you're right when you say that pure electric doesn't work for airplanes that have a lot of people and a lot of range, just because battery technology is not there.
it doesn't look like it's going to be there in any type of realistic future.
The
Basic science isn't there yet.
The fascinating thing about a battery is that I was speaking to somebody who makes electric motors, and I asked, this gentleman was involved with the electric beaver, the e-beaver as they call it, and the fuel tanks in the wings are replaced by batteries. And the interesting thing is that, of course, when an airplane takes off, it has a takeoff weight, then there's a landing weight. With a battery power, that's the same. You don't get rid of weight as the plane flies. And of course, that's awkward because airplanes don't like weight.
That's a critical. I was going to say that's a critical term in the Breguet range equation, right? Is the fact that the plane gets lighter is a significant reason or thing that contributes to the range of an aircraft. So yeah, you're absolutely right.
Any last thoughts, gentlemen?
Well, I'll just remind you that we did build a hydrogen engine at Pratt & Whitney in the late 1950s. It was called Project Suntan, and it was done to support Skunk Works, and it was for a military aircraft that was never actually built. But I think we built 3 of them, and we did some ground demonstrations. Very unusual cycle. It was a liquid hydrogen engine that expanded through a turbine and then had an afterburner. But Pratt & Whitney has designed and built a hydrogen engine. It was just 60 some years ago.
Yeah, it was 2. There were 2 ground demos.
2 ground demos.
Where are those engines today?
I don't think we know.
You mean what goes into the Skunk Works stays there, never comes back?
Well, that's the problem. Those were deep, dark programs in the Cold War era. So they disappeared. But as a tidbit, a lot of the hydrogen propulsion technology for rockets, the RL-10 engine, came out of that research and development activity for the Suntan engine.
Gentlemen, thank you so much for visiting with me.
Thank you very much.
Yeah, thank you.